unfortunate thing is I was expecting to go after another presenter, so you got me a bit off guard, but that's okay, no problem. So my name is Alex, so Alexander from AMD, so whatever you prefer, I'm informal anyway. So I'm part of the server BU team at AMD. My focus is European region, so I'm based in Munich and I'm supporting our customers, partners, ecosystem on technology, basically kind of a, you can call a data center technologist for the European region. So with that, for today, we have some topics on optimizing the performance and memory subsystem on the AMD-based systems. So we'll talk more about the NPS settings, the different subsystem on memory and the controlling of that with memory interleaving on AMD platforms, especially across the latest generation of EPYC, our server CPUs. But before I start, maybe a couple of questions to you. Random one, maybe you're a bit tired of those questions, but how many of you guys know about AMD overall? Yahoo! How many of you guys use or have tested before AMD-based data center products? Okay, good. Is everyone happy? Okay, nice. So I won't talk product too much from the CPU perspective. If you want, I'm more than happy to exchange and talk about that. But the first thing is we have been coming from a long way of, let's say, launching product in history. So from around 2017-18, we launched the first generation of EPYC. So that's, well, non-technical slide. I think starting next one, it's going to be more technical, more and more architectural. But I wanted to start it with simply where we are now and our focus area, which is the consistently expanding the products we have and solutions offerings on the market, and also supporting the open ecosystem and overall ecosystem enabling solutions. So kudos to, I mean, Benny is not here, but kudos to Jonathan team and the team on AlmaLinux side for testing and qualifying some of our like AMD-based systems. So you know that it runs perfectly well, so that's good. But then the most important thing is the trust. So we have been consistently executing on the roadmap and we'll bring the next generation later this year. That's it. The key thing on the CPUs is the three main pillars of the architecture design, which is scalability, performance, and energy efficiency. So for now, and I've been around AMD EPYC products since the first generation. Any of you have tried 7001 or codename Naples CPUs before? Ah. Well, I know Peter, but Peter will tell you, and don't know your name, you might remember, and you might be able to tell others as well how peculiar this product was, considering the default NPS4 and like the CCD0, which you need to power up and then redistribute. So considering especially enterprise space, so less of an HPC, it was not a product ready, really ready for that segment. So we have come a long way. And from scalability perspective, that's simply a number of cores you can get within the system, so scaling between 1 and 2 sockets. We've also expanded the memory footprint now to 12 memory channels with the 9004 and 9005 series, which is something I'll talk more in details about and how to optimize that, but also spanned across different core counts leading performance. So meaning whenever you choose any type of, any core count CPU from AMD, you get the best performance, best efficiency out there. So, which is good. And what I'm referencing is usually the public results you can find, which is spec in, spec FB, traditional spec rates, which are all available there. This is usually how we measure performance. So, So a quick reminder of different series of processors we have, because there is a different subsystem behind it, meaning the number of PCIe lanes and the number of memory channels. But I won't stop too much on that, just a quick reminder. Now, let's go into the SoC. The topic of today is balancing the memory and optimizing performance on AMD systems, how to do that, what I want to focus on. The first thing is this slide, which is a bit too busy. But this is the pretty much the schematic design on the SoC of the 9005 series. So you see the I/O die and then the CCDs or complex compute dies overall where the cores sit. So, and I wanted to show you that specifically as we go further than into the memory subsystem from one specific perspective: the application performance and ability to core pin particular workloads within the SoC is quite large. So overall, everyone is familiar with the NPS, NUMA per socket, or NUMA domains, so non-unified memory access. I assume yes. So with that being said, the CPUs go with 1, 2, or 4 setting, and that's something I will talk more in detail specifically, but just thinking about it, if you have particular technical workloads you're running, or the in-house software development, I mean, if we still have Alex and the CERN team here, they highly likely will be able to comment on that in details. But as we have different setting of NPS and the core allocation, you can pinpoint the cores and optimize the latency to memory in those particular quadrants down to 4 NPS. So it's visually very easy to see on the CPU, which I have in my right pocket. It's just too many things in my hands. But you will be able to see on the back end of the CPU, basically 4 quadrants, which you can use for the NPS setting. And in reality is, and this is what I'll show on the next slide as well. So when you pinpoint the memory, depending on the memory usage, so as you can see here, I mean, that's a real CPU. So, but the background of it, the socket, you have a line out of the 4 kind of quadrants, and that's the best optimization setting in terms of the really core pinning and decreasing the latency on the workloads and per core, core to memory access type of application. So, but how to do it, again, we'll talk more about. This is overall SoC design, so it's all the features, all of the details around there. I won't stop and go through each and every one of them, but you have options. This is even more detailed. And on 9004 and 9005 series, we have 12 memory channels. So reality is, as I showed you the CPU as well, you have one I/O die in the middle. So coming back to this one, for example, you see the middle I/O die. This is where the memory channels are. This is where the AMD secure processor is, which powers the confidential computing, for example. I'll touch upon that too. And this is where the PCI lane spun out is, so basically the interconnectivity lane. So this is like a one pillar chiplet design approach. And then you have cores all around it. Reality is that you have memory channels connected to those quadrants, as I mentioned, depending on the part. So sometimes, so going into very, very like low level of SoC details, you will have different number of those complex compute dies depending on the core count. And so there might be 2 of them activated, there might be 8 of them activated. But logically, if the CPU supports NPS4, it means that all of those quadrants are activated. And so the best or lowest latency, the best performance per core, you will achieve with NPS4. Reality works this way. So I think I can do this as well and show technology. So you have the memory channels and interconnectivity, you have the I/O die and connections, and then you basically have the cores. So as it's in the kind of a multiplier of 4, you have then 12 memory channels separated with 3 memory controllers or channel controllers on each and every side. What it means is, if you use NPS1, you have 1 pool of memory. That's easy. But if you then go deeper and optimize the performance and latencies, then you can allocate those cores closer to memory. So you avoid going from here to here. Simple as that. This is one of the things you can do if you want to. It's possible, it's available. Not a lot of people do that really, and a lot of people expect the software already they're using to do that instead. It's all about scheduling and so on. So it's, for many of you, it might not be applicable, but Benny asked me and Jonathan asked me to give you some of the technical details which might be relevant. So I'm combining this with a couple of other things. So this is one thing and how it's structured. If you want to go deeper into the CCD, for example, design and the L3 caches, so basically where you can get, or which level of latency and which level of performance you can get between the cores to memory through cache. Same goes here. So the lower amount of hops you have between the cache and memory, the lower the latency is, hence the optimization on the quadrants. That's pretty straightforward, I think. But it's important so you guys know how it's all structured, and that's why I put it here. So Benny will have the slide. I think, Jonathan, correct me if I'm wrong, but you will redistribute it as well with the audience, so you can see it yourself later on study if you want to. But coming back to this one, you will see how it's structured, the highest parts, and also the kind of a design on how many CCDs we use. The logic is, let's say if it's Zen 5, for example, that goes up to 228 cores. So with 16 CCDs there, you can then easily calculate the cores per CCD and then go from there. Like that's the logic, just combining multiple CCDs on one package so you have a chiplet design full solution. That's all. There's one another quirk in BIOS settings across all vendors, more or less, which is a small tip. I don't have a slide for that specifically, so I'll just leave it here. If you go in, there are two power settings. There's power optimized and performance optimized. Which one do you think will give you more performance? So they know, and Jonathan guessed correctly. Yes, so it's power. What it means is it will let the board draw more power to the CPU, so you have a range of higher frequencies and stable, like not stable, this is not the right word, but a stable flow of power to achieve the highest performance possible. In the performance setting, it's stable performance, but not necessarily the highest power draw. So that's one of the quirky things in BIOS, and I have no idea why specifically it was named this way, but we have had some interesting conversations with customers about that. So we also have different tuning guides. I'll save the links out there in the end of the presentation. So if you want to tune in for a particular OS or for particular workloads or for particular use case, or for example, lowest latency, we have detailed tuning guides on how to do that because there's like a C states control and more of that. So, but going forward, where is it? Here? Yeah. Okay. So this is the thing I was trying to explain, right, in terms of the memory channel population, so an NPS settings. So as you can see, and as mentioned, so you have unified memory controllers, which are then in the multitude of 3, separating 12 memory channels across them all. So, and as you go in and try to optimize things, as long as you can and are interested to doing so, you can. If you don't need that, use NPS1, use old memory. There's supported 2, 4, 6, 8, 10, and 12 memory channel interleaving. Simple as that. So it depends on what you want to do. With that being said, we talked a lot about the NPS setting and memory. We have done some work or some homework, however you want to name it. So our team on the engineering team has done different sizing on the memory and performance comparisons as to the population. You will understand what I mean. I mean, I don't need to explain the current market situation to anyone with memory pricing and provisioning and stuff. So yeah, don't need to do that. So a couple of things to mention. So by default, the traditional reference board or architecture we have is 1 DPC, which is 1 DIMM per channel. So we have 12 memory DIMMs, so 12 channels. This goes into socket system to 24 DIMMs. We can support 2 DPC as well, which is 2 DIMMs per channel. But that would be in the 2-socket system, 48 channels, which is, as you can imagine, a pretty hard thing to fit in a 19-inch rack chassis. But there are solutions which can do that. So for example, one from ASRock rack in here, but that's usually very niche and limited. So majority of the 2P platforms would be 24 DIMMs. This is important as we will then calculate the different size memory size scenarios. So I'll show you that. But in general, if you look into the 1-socket platforms, then you will have an opportunity, because that fits, to have either 12 or 24 DIMMs. So you have a pretty high rate of memory per core ratio, however you want to size the system. So, don't know, memory per core, per socket, per system, per cluster, doesn't matter. So, with that being said, not all of those available channels should be populated. I know the usual, like, oh, to achieve the best memory bandwidth, you need to populate all, and that's true. You can't go around with that. But many people do not necessarily need that. And plus, if you look into the lower core count segments, 8, 16 cores, 32, many of them, you will just overfeed the CPU. So you will not be able to utilize memory like with all the channels anyway. So it's always a balance of things. So provisioning in terms of the memory. So couple of works, yeah. So couple of considerations. First, there's memory module pricing. So right now on the market, usually 64 gigs is DIMMs as the best per core, or sorry, per gigabyte ratio on the memory. So we don't see this particularly changing soon. But overall, there are different sizes. And there are different cost optimizations available across that. So for example, if you really need a big memory pool, you can use the bigger amount of DIMMs, but with lower sizing. But again, I don't need to explain you that. So there's always a consideration between 1 DPC or 2 DPC, at least across a lot of enterprise customers, because they usually think about capacity rather than bandwidth. I would say many of you, especially in the HPC space, would think about bandwidth rather than pure capacity. So it really depends. But then we also have a lot of our partners providing their own configuration rules. And what we have observed with many is, it's going to sound very stupid. You will understand why. But unfortunately, we see this constantly. So for example, if you open the memory population guide on our competitor, so anyway, let's say HP for an example, like open the memory population guide for Intel Xeon, open the memory population guide for AMD EPYC, populating all the memory channels will give you 100% bandwidth. Sounds logical. Great. But none of those guides tell you how much bandwidth you will have and what's the difference. So we have perception from some people that populating 12 memory channels on AMD and populating 8 channels on Intel is the same. It's not. I mean, it's just mathematically not, because you have the same speed but just more memory. So we have by default better bandwidth. But this is important to note, because if you really think through it, there are different optimizations on the, again, bandwidth to capacity ratio you can do, even populating not all channels. It really depends on what you need. But sometimes it's kind of lost in context. And this is what I'm talking about. So we've measured together with Phoronix, that's the next slide, so Phoronix team, we've measured the performance on different benchmarking and workloads across, let's say, using 8 to 12 memory channels. Obviously, in SpecFP, floating point rates, which are usually memory bound, or HPC type of workloads, it is impactful, the difference, of course. But across many of other, like TPC, for example, some of the database benchmarking, some of the, I would say, traditional integers sometimes impacted, but not that much, not that drastic. Across many other workloads, which you can see on Phoronix as well, the implications on performance are not that high. So it does matter. So then you just find whatever workloads you use or trying to do and see if it economically makes sense to run it on 12, on 8, depends. But you have an option. And this is Phoronix results. So basically going through this, you will be able to go to the Phoronix website. You can Google it right now. That's not a problem. All publicly available. So you will get through the results on each and every workload they test, which is usually archiving, blockchain, virtualization database, a bunch of others. So there's a bunch of things they do, and this is what they were able to see. So what is like 5% better on average geometric mean. So if you use many workloads or many applications running on the same machine, you have more options in terms of the memory balancing. But if you use one particular workload, of course, you need to think through on how it will be performing. And especially if it's HPC modeling, CFD, EDA workloads, it's all the memory channels and the frequencies are also important. So usually go with 1 DPC there. Now, we've also prepared that, but again, this is nothing of extraordinary. You can do the same yourself, but might be saving you time. So we've put up the total capacity, the DIMM capacity overall, based on the number of memory channels we have, and created this matrix in terms of population. So you stick in, and I need 2 terabytes of memory. This is the balanced options on how to go there, or like 1.5. It's a simple matrix table, so that's all. And at the same time, we have done this, which is sizing on gigabyte per core. If you need to take a photo, I'll go back. So it's easy as that. So it's a matrix of gigabyte per core, simple as that. So it's again, just hopefully saving you time, because you can calculate the total size of memory divided by memory channels anyway yourself. So it's not a big deal. But we've done it. So we've done also different testings around it. And this is what I'm going to show you as well on 1 to 2 DPC performance, as I still have some time. But logically is, no matter how you size it, for example, if you do any type of virtualization and size it per VM, or with over-provisioning or without, that will help, just to save time calculating it yourself. But honestly, it's not rocket science. Not flying a plane like Jonathan does. So. A bit easier. So 1 DPC versus 2 DPC performance. So setting the scene would be this. This is again all public info in terms of like generally comparing the subsystem, the memory subsystem, between the latest gen on our competition and latest gen on ours. Simple as that. So as mentioned, there are not many 2 DPC platforms on 2 sockets we have. They're very limited. So that's why we'll focus across all of it. But you see that going to DPC for us, considering the memory signal integrity, overall with 2 memory channels, we will drop the speed dramatically. So it goes to 4,000. So the key question our team had was, how much does it really impact the performance of common workloads and generically across the ecosystem? How much of the impact really is there, and how much the workloads do depend on speed of memory? Again, some of them will do more, some of them will do less, but that's clear. So, and then underlying thing with the memory population guides I mentioned, look at 1 DPC or 2 DPC, doesn't matter. The bandwidth on AMD with 12 memory channels is just by default higher. The speed is the same, amount of memory channels is higher, the bandwidth is higher. I don't know what else to say. It's straightforward. So, but a lot of people miss it out, especially if the documents do not compare one to another. And that's what I wanted to really just to highlight. Every 2 weeks I have this. So better to do that. Also from the pre-sales. So that's why it's not just like a sales thing. So, like people operate sometimes on perceptions and they see one document, oh, but that doesn't, how it goes. It's much cleverer than me, you know. So done the same thing with Phoronix, so you can find all of those results as well. And obviously, we have seen in some of the HPC workload, I would say in many of them, the performance impact with higher memory speeds is significant. Can be 10, 15%, can be more, of course. But on average, once again, geometric mean of 37 benchmarks with Phoronix, it was around 2%. Many enterprise customers we know buy capacity, not specifically bandwidth or speeds. That's why you have option across everything. So that's just a reminder of what we have, how we size it, and highlight to the results you can find yourself out there, and not hiding with the footnotes of this is the special testing type of thing. This is all you can find. Same goes for spec results. We even have tools how to find them faster, just to save some time there, but it's okay. The last thing I wanted to mention, I still have some time left, is confidential computing. We had a keynote around that. I won't assume that any one of you has joined it. It was at 11 a.m. today. But I'll give you a quick rundown on it, and that's all around encryption, specifically, or how to enable confidential VMs or confidential computing. So with that being said, it's not a new topic for us overall. So from 2017, when we launched the AMD EPYC processors, we have so-called AMD Secure Processor. Within the I/O die, technically, I think, within the I/O die, we have a small ARM core which manages the security keys. Now it's more than thousands, more than 1,000 of them. What can you do with those security keys is important, and this is what I will cover in the next slide. It's encrypting memory, encrypting VMs, and encrypting the IO lanes. I'll give you some details there. But this technology has enabled and grown throughout the years, and has enabled such things as Microsoft Azure confidential VMs or Google confidential computing. How? Because you turn it on from the silicon root of trust perspective and you get the encryption readily. So we've enabled also the ecosystem as well to do that. Different hypervisors, different OS support. I have also a guide on how to do it. So there's a link out there on the last slide around that topic. So you can come in and see step-by-step instructions as to where it is supported, on which level, guest, hypervisor, or guest or host, and then go through the details. But 5 technologies, I'll kind of mention 3, 4, because some of them are similar. It's just the expanding on the basic technology. And those are the product lineup. So if you take the latest generation, obviously everything is available. TSME, or Transparent Secure Memory Encryption, is a bias stick. Basically gives partial or full memory encryption, so it's data in use, from BIOS with 1-2% performance impact. That's all. Just turn it on, encrypt the memory, you're good. So that's to prevent the fancy attacks like freezing in nitrogen the memory sticks and reading the data. Kind of comes from there. So SAV is secure encrypted virtualization. And then there's encrypted state, and then there is the secure nested paging, which is, I would say, a follow-up from the traditional SAV initial kind of design. And all of those things are about isolating VMs from one another and from the hypervisor itself. So it's creating a trusted execution environment, basically, where you exchange encrypted memory data with encrypted VM. So you have this layer. And then you also have, for example, reverse map table, which is the secure nested paging, to mitigate such attacks like rollback of the firmware software. So you always have an access, not access, but the owner privileges in the SNP, which will then correct or allow or not some type of changes within the system. So you have this mapping to mitigate the rollback attacks. And Trusted IO is based on the open standard, which we developed with CXL. TDISP, if I remember correctly, that's basically an encryption of the PCI lane. So if you go further then into the confidential AI, if you have a GPU, which usually then also fits through an orchestration with the CPU within the system and memory, you need to encrypt it all, have a also TAE, or trusted execution environment, across all of the devices, and that's the next step technology around that. So this will be expanded in the future as well, but once again, it's supporting the open source technologies, supporting the open ecosystem. It's TDISP in this case with CXL, and we've done many of such things before and will continue to do after. As promised, visit the Confidential Computing website. There is a bunch of information there, which is quite useful. There is an ebook. It's more an ebook, so fine. But there's also, we have so-called technical information portal. For those of you who haven't visited it yet, this is the area where we'll have a lot of tuning guides, memory population guides, platform development guides, different types of technical info. It's usually docs.amd.com, if I remember correctly. But there's this guide, which is using a SAV with AMD EPYC. There's a number of them, 58, 58, 207. It's the document number. And this will go through where is this supported, which technology, how to enable it, where to enable it. So it will go step-by-step guide. With that, there are also other tools. So we have different webinars, and like it's Meet the Experts webinars, but they might not be extremely technical. So feel free to reach out to us or meet us on different events. So we're present usually in many industry events, including ISC, SC, Computex, CloudFest, and WC, and more. And we have also those tools If any of you want to know like what would be recommended AMD processor, there are tools there, and also calculating the TCO if some of you do any type of business stuff as well, or sizing the configurations, that's available. And the server tech docs is kind of replicating the docs I mentioned, like the technical information portal. So there are more details available. Just go in, check it out, and if you need the NDA access, let us know. We can follow up on that as well. With that, I'm right on time. That's me in Lumi, which is a supercomputer in Finland. You know my name. I also go by that EPYC guy because I can't go anywhere without the CPU in my bag, pretty much. Anyway, it's just a fun note. But thank you. I'll close there. In case any questions, I don't want to postpone the speaker. I'll be here for some time as I need to leave right after. Thank you very much.